In this next section, we're going to introduce the concept of the TCP finite state machine. And where this is really beneficial is, for example, let's say you're doing some sort of a debug on a router or some other kind of device. And at the moment you're doing the debug, it tells you that TCP is in a certain state. Like maybe it says it's in the listen state or the fin wait 1 state. If you don't know what the finite state machine is, then you won't understand what is that state telling me? Where in the process of a connection is TCP right now? Is it in the process of building a connection? Is it in the process of terminating a connection? Is it waiting for something? And if so, what is it waiting for? So that's what we're going to go through now. Now let me do a little bit of a disclaimer here. The full TCP finite state machine is massively complex because there's a huge quantity of variables that could happen at any given time during a TCP connection. So I'm going to show you basically the perfect example, assuming that nothing goes wrong and everything goes smoothly, the common states that you would see. So, first of all, if you've never heard of that term finite state machine before, let me just take just a brief moment to explain what is meant by that. So protocols, whether you're talking about a routing protocol or TCP or anything that moves through transitions are designed to do something, typically should move start to finish in smooth, predictable ways. So a finite state machine is a diagram that graphically displays this process. Instead of verbally telling you or writing it in like textual form in a paragraph, it's a diagram that shows you boxes and arrows that says, okay, here's where you are right now. If this thing happens right here, then you're going to move into this state right here. So it's just a graphical representation of where a protocol happens to be in time, what event preceded it that caused it to be where it is right now, and what things could happen afterwards that could cause it to move to a different state. So finite state machine composed of states, the current status of the protocol, where is it right now, what's it doing? Transitions, moving from one state to another, so that's usually indicated by some sort of a line or arrow, that's a transition. An event, sometimes called a trigger. In other words, something has to happen in order for it to move from one state to the other. Maybe in the case of TCP, maybe it's a missed acknowledgement and a timer expiring. Maybe it's the cause of an incoming sync that's received. That's the event or trigger to make it transition to something else. And then an action. What's it going to do when the trigger or event happens? Is sometimes a trigger, sometimes you'll see finite state machines and they'll have like an arrow that is like a loop. It'll say, okay, this arrow represents I'm in this state right now and something came into me, but I'm not going to do anything about it. I'm not going to take any action. I'm just going to stay in this state even though there was some event, some trigger. So the objectives of this is just to display the transitions and where TCP could go, what it could do based on various triggers, various events that could happen. So let's narrow this down a little bit. The primary flags that we're going to be looking at are the sync, the ACK, and the fin flags. So all three of these are flags within the TCP control section of the header. So let me just go back for a minute in case you forgot what that was. Back to here. So the code bits. Sometimes it depends on what diagram you're looking at. Sometimes this field is called flags. Sometimes this field is called code bits. But basically this field right here has got several bits in there that can be 1 or 0, and depending on what the setting is, for example, there's a certain bit in there that if you set to a 1, that means sync. That means I'm trying to synchronize or start a connection with you. So another flag in there that says fin, which means I'm trying to finish or terminate a connection with you. So as we go through this finite state machine, we're really going to be concerning ourselves with what bits are set right here. And when we see a TCP segment come in that's got one of these bits set, how's that transition us from one state to another. So we're going to start with the top. Let me expand this a little bit. So this blue box here is representing the initiator, right? This is the person this is the device that's performing the active open that says, some application has informed your CPU, I need to make use of the services of TCP because I want to communicate to a web server. I want to establish a connection with an email server. So this is the initiator. So it starts out at the closed state, meaning you don't have any kind of TCP connection with anybody right now. Okay, so what happens at this point? So an active open happens. So during this process, the application, the upper layer application, is notifying the CPU and notifying TCP saying, hey, I need to use your services. So a transmission control block has to be created. We've talked about that. And then we're going to create and send a TCP segment with just the TCP header. There's no data in it. And the thing that's special about this particular segment is that within those code bits, the one particular bit called the sync bit or the synchronization bit will be set to a 1. So we call that a sing or a sync. So as soon as we send that, we now move from the closed state to the sync sent state, which, just like it sounds, it means we have sent a sync. So if you're ever looking at a debug or something and it tells you that your current state is sync sent, it's pretty much exactly like it sounds. Now, one thing about this, if you're in the sync set, you actually know two things. One thing is pretty clear. You've sent a TCP header with a sync bit set. The other thing it's telling you is that you are the initiator. The device that you're looking at right now is the one that performed the active open. That's not as clear by seeing the sync set, but you're only going to see this particular state in the initiator, not in the responder. We'll see the responder in just a moment. Okay, so now hopefully, if everything goes well, you will receive a sync plus an ACK from the server, from the responder. You will in turn send your final ACK back. So you're basically saying, okay, server, thank you for acknowledging my sync. I'm now going to acknowledge the sync that you sent me. And so now you move from the sync sent stage to the established stage. Okay, so now you're in the established state of TCP, and established basically means your three-way handshake is complete. You've negotiated everything that you need to negotiate. You're ready to start encapsulating data into segments. Okay, now what about from the responder's perspective, that server is just sitting around waiting for incoming connections? Okay, so it's going to create a passive open, which, as we've talked about earlier, means that he sets up a transmission control block that's only partially filled, right? The socket information doesn't have all the information he needs. He doesn't know the IP address of who's going to talk to him. He doesn't know the source port number of who's going to be talking to him. So as soon as he sets up that transmission control block, he now moves to the listen state. So what is this telling you? Well, let's say that people were complaining and they were saying, hey, I can't bring up this particular web page. So you go to your web server and you've got some way of looking in the registry or something to see what particular state it's in right now, what TCP state. So if you saw that was in the closed state, that would tell you, okay, well, he didn't perform the passive open. He did not set up the transmission control block. So that would mean basically one of two things to me. Either like the Apache web server program or whatever the web server application is that you're running hasn't been started. It's just turned off. You forgot to start it. Or there's some kind of a bug where the server application, the web server, the Apache, whatever, started up, but some sort of bug where it did not notify the CPU, which in turn notified TCP, that a transmission control block needed to be created. I don't know that would ever happen necessarily, but you can see those two things have to happen. Passive open means the application itself wakes up, it becomes aware. Second part of that is it has to tell TCP, reserve some memory, set up a transmission control block, and that puts it in the listen state. Okay, he's listening now. He could be staying in the listening state for hours or days or weeks. He's just going to sit around waiting to see if anybody's going to talk to him. Now, hopefully, eventually, a sync comes in from some laptop out there. The server sends a sync plus ACK. Now notice all this time he's still in the listen state. And then he moves to the sync received. Okay. So receiving a sync, sending the sync plus ACK now moves him into the sync received state. So what's the last thing that we're looking at here? Well, he's received a sync. He sent a sync plus ACK. Now the server is saying, hey, I came up with my initial sequence number. I put that in the sync plus ACK I sent to you. Client, you need to ACK it. Client, I need to know that you saw the initial sequence number I came up with. Hopefully that will happen, and the client will send you the final ACK, so that's the third part of the three-way handshake. And so now you can move from the sync received to the established state. So that is normal connection establishment and the various states in the finite state machine that things could move through. So just a couple of takeaways from this. Once again, remember, if you're on a device and you see that's in the sync sent state, you know you are on the device that did the active open, that initiated the session. If you're on a device that's either in the listen or the sync received state, that's the responder, typically the server. Okay, now what about closing a connection? This gets a little bit more complicated, not too terribly much, but a little bit. So once again, let's start in the top box here, which is the initiator. So you've got some website open to INE.com, and then you go to that particular tab in your browser and you click the little X to close that tab. So you are now the initiator. What happens? So you're currently in the established state. As soon as you click that tab to close it up, let me go back here. So at that point, the application process, Firefox, Chrome, whatever it is that you're using, has to notify TCP, I'm done. I don't need you anymore. So that's what we're seeing here, receive an application close. At that point, TCP's job says, okay, I need to send a FIN message. Now this, once again, just a TCP header, no data in it necessarily. There could be data in it, or there could not, but the main thing is in the TCP header, in the code bit section, now there's another bit that we flip to a one called the FIN, or the finished bit. So we send that, and we move to the FIN wait 1 state. Now let me pause here for just a moment. In a graceful finish, when TCP gracefully finishes, what we're going to see, it's sort of like the three-way handshake. Think about the three-way handshake. Both sides had to send a sync. Both sides had to acknowledge each other's sync. And then we could go to established and we could move on our way. Well, in a graceful close, same type of thing is going to happen. Both sides are going to confirm the closing by sending a FIN, and both sides are going to have to acknowledge each other's FIN. And then the session can well and truly be closed. So when we're in the FIN wait 1 state, we've now sent our FIN. So one of two things could happen at this point for the perspective of the initiator. One thing that could happen is that we actually receive an acknowledgement for our FIN. Great, so the other side got it. He knows that we want to terminate this connection. The other thing that could happen is we actually receive a FIN from the other side. So in B here, option B, this is where both sides are closing at the exact same time. It's sort of like what's called a simultaneous close, where we both send each other's FINs at the same time. Okay, now, so let's start with A up there. If I receive an acknowledgement for my FIN, my laptop can't say, okay, I'm done, I'm finished, because remember, it's not only do I have to send him a FIN and get an ACK, I'm expecting the server to send me his FIN as well. Now at this state right here, in the FIN wait 2, if you see that, several things could be happening. Number one, this means I've sent out my FIN, he acknowledged it. Okay, great, he knows I want to close. Haven't received his FIN yet. So what that tells me, so let's say the initiator here is me, my laptop. If I'm in the FIN wait 2 state, that means the server, the application running on that server, isn't quite done yet. Okay, so TCP has notified the application on that web server or that email server or whatever that the remote client wants to shut down, wants to close this. And the application on that server is saying, well, hold on a second, I'm not done. So right here in the FIN wait 2 state, I could still be receiving stuff from that server. If this is a web server, maybe the web server is still going to send me a segment or two before it's finished. I can't send anything to him. If my client is in the FinWait 2 state, no more stuff can come from my client. I can no longer upload data to that server. I've told him I'm finished, I have to be finished. But until he sends me his fin, he could potentially still be sending me stuff, sending me segments. Now, what if we have a simultaneous close where, within milliseconds of sending my fin, bam, I receive a fin from the other guy. So before he even acknowledged my fin, he sent me his own fin. Okay, well then my job is to ACK it, and I move now into what's called the closing state. All right, so let's go back up to number A, which is more likely here. I send a fin, I get an ACK bat. So now I'm in FinWait 2. So what's the next thing I would normally expect? Well, I would normally expect after some amount of time, that server to send me his own fin. So eventually the server's application, Apache, Microsoft Outlook, whatever it is going to say, okay, you're okay. You can close the connection to the client. When TCP is aware of that, the server will say, okay, I'm now going to send a fin back to the client, which I have to ACK. And now that puts me into what's called the time wait state. And I'll talk about that in just a moment. If I'm in B here, where the moment I send a fin, I immediately got a fin back, it was a simultaneous close, then I sent him an ACK, he still has to acknowledge me. He has to acknowledge that he saw my fin, because maybe it got dropped. So in the closing state, there's a possibility that my fin never actually got to the remote guy. So I need acknowledgement that it got there. He does acknowledge it, hopefully. And once again, that moves me into the time wait state. And then from time wait, after a timer expires, we now go back to closed. Let me talk a little bit more about the time wait, because if you're like me, you're probably wondering, well, what is that timer? How long would that be? I'm kind of curious. All right, so let's first of all talk about the RFC. According to the TCP RFC, the time wait state is supposed to wait twice the length of another timer called the maximum segment lifetime timer, MSL timer. It's supposed to wait 2 times that. And the TCP standard defines the maximum segment length timer as being 2 minutes, 120 seconds. So because time wait is twice that, the original RFC said you're supposed to stay in the time wait state for 4 minutes, twice the length of the maximum segment lifetime timer, 4 minutes, which is a long time to wait in the time wait state before you're closed. Now, you as a human being, you could probably care less. I mean, the moment you close down your tab in your browser, or you close down, Microsoft Outlook or whatever, you're done. You don't know that TCP is doing all this stuff in the background, but TCP in your CPU and everything could potentially be waiting up to 4 minutes before it finally closes. Now, I've also read that vendors may choose to do a different timer. So in reality, Microsoft, Linux, Unix, they might not actually wait 4 minutes in the time wait state. They might wait probably less than that. So that's the initiator. That's assuming like your client closing down your web-based tab or whatever. Now, what about the responder? So let's look at the responder state. So he's currently established, so now we're looking at the server. So the server is established with you. All of a sudden, oh my gosh, that client I've been talking to, I've been sending these web pages to and MPEGs to, he just sent me a fin. Okay, client doesn't want to talk to me anymore, so I'll send him an ACK back. And now that puts me into the close wait state. Now at this point, TCP has to turn around and talk to the process, the upper layer process, and say, hey, that client that you've been talking to, that you've been exchanging MPEGs or JPEGs or whatever with, he doesn't need you anymore. He's done. He's not going to send any more stuff. So eventually the process, the upper layer process, will send a close, and now the server can send its own fin back to the client, which moves us into the last ACK state, because just like it sounds, the server says, okay, I am waiting for one final acknowledgement. I need that laptop, I need that client to acknowledge my fin. At some point, you'll get that acknowledgement, and you can move directly from last ACK into closed.